Recursion is when a piece of code calls itself over and over again, breaking down the problem into smaller and smaller chunks with each iteration. Eventually, the problem is small enough to be solved and then it goes in reverse. Now, how that works in practice is best explained with an example. So in our first example, we're basically doing something that a loop could technically do better and easier, but in this case, it's going to really explain how recursion works. So here we're creating a simple function that takes a number and counts down from that number to 0, one at a time. So in line 10, we call our function countdown and we give it a number 5. When this final line is run, we call the function countdown and we hand it the number 5. Now at this point, the function takes an argument of 5 and it checks, is 5 equal to 0? Now this is called our base case. Since 5 isn't equal to 0, we move on to our else block. And here we're printing out the number 5 and we're calling the same function countdown again with n minus 1. So that's 5 minus 1, that's 4. Now this is where the recursion comes in, because we're calling the same function inside itself. So once again, we're running the function and we're checking, does 4 equal 0? Because remember, we did 5 minus 1, that's 4. 4 isn't equal to 0, so we run the else block. We print out 4, and then we run countdown of 4 minus 1, which is 3. Same thing repeats. Is 3 equal to 0? It's not, so we print out 3, and then we run it again, and so on, until eventually we are going to be running countdown with an argument of 0. At that point, when we check, is n equal to 0, we are going to run the base case. We're going to print out done, and that will be the end of our execution. Just to prove this works, I'm going to right click over here, run this code, and here we go, we've got 5, 4, 3, 2, 1 and done. And on the right hand side over here, you can see exactly what's going on while this is running in the background. That brings us on to our second example. And here too, we're doing something that could be solved more easily with a loop. But once again, this is going to really hammer home how recursion works and what it's capable of. So we're creating a function which adds up all of the values inside an array from a given index to 0. So here, where we're running the code, we're creating an array with 5 numbers in it, 1, 2, 3, 4, 5. And then we're printing out or console logging the result of running our array sum function given the array we just created, that's numbers, and given the index value of the last number in that array. Since indexes start from 0, this is the length of that array minus 1. Now if you loop back to the first line to see how this is actually running, in our first line we're creating the function header and giving it 2 parameters. The first is the array and the second is the index from which it needs to add up all of the values. Now first we're going to check, once again, the base case. Is the index less than 0? If it isn't, we're moving to the else statement, where we are returning the value contained inside the current index of our array added to our same array function given our same array and an index value 1 less than what was initially given to it. And if you run this through inside your head, you're going to realize that every time this function is run recursively inside itself, the index value goes down by 1. So eventually we're going to end up with an index value of 0, at which point we return 0 and we can end the execution. Now on the right, once again, you can see that what we're doing is we're creating this chain of functions within functions that all need to be run. Eventually, when we get to our base case and we return 0, we can go back through the chain and finish our execution. Again, just to prove this works, I'm going to run this and we get our result of 15, which if you do the maths, 1, 2, 3, 4, 5 added up is going to be 50, which takes us to our third example, factorial. Now this is a use case where recursion is actually one of the most efficient ways to achieve this thing. So a factorial, if you don't know, it looks something like an exclamation mark and it symbolizes multiplying a number by every number below it up until 0. So a factorial of 5 in our example would be 5 times 4 times 3 times 2 times 1. Factorial of 10 likewise would be 10 times 9 times 8 and so on. In our final line, we're printing out the factorial of 5. The function takes an argument of 5 and it checks the base case. Is 5 equal to 0 or is 5 equal to 1? So if our argument isn't equal to 5 or 1, we're running our else block. And inside our else block, we're returning our argument n multiplied by the factorial of n minus 1. Again, calling the function inside itself is where the recursive bit comes in, and using an index of n minus 1 is going to eventually reduce the index down until it is 0 or 1. At which point we're going to run our base case and return 1. And then we can go back through the chain, multiply all our numbers as shown on the right, and then get our result, which we can double check is 120. This takes us on to our fourth example, Fibonacci. Now the Fibonacci sequence is a mathematical sequence of numbers which appears throughout nature everywhere, and the next number in this sequence is always calculated by adding up the previous 2 numbers before it, with the sequence starting with 0 and 1. So if we're starting with 0 and 1, the third number is going to be 0 plus 1, which is also 1. The fourth number is going to be 1 plus 1, which is 2. The fifth number is going to be 2 plus 1, which is 3, and so on and so forth. Once again, we're testing our code by printing out the result of our Fibonacci sequence given an argument of 10. Now what's going on in the background is we're taking our argument of n and we're checking, is n less than or equal to 1? If it is, that is our base case. If it isn't, we're returning the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. So remember what I just told you about Fibonacci. The next number in a sequence is worked out by the previous two numbers before it. So if you want the 10th number in Fibonacci, you have to work out what the 9th number plus the 8th number is. And to work out each of those, you have to work out what the two numbers before those are, and so on and so forth until you eventually hit 0. Now in a real life use case, this is a really inefficient way to calculate Fibonacci numbers, but it does do an excellent job of demonstrating how recursion can work. Once again, on the right, you've got a run through of exactly how we're going to be calculating our Fibonacci of 10. And just to double check that this does actually work, we're going to run this code and we're going to get 55. That is our 10th Fibonacci number, which brings us on to our 5th example. This is our most complicated example because it looks at something called a tree. Now tree data structures in programming crop up everywhere. They're inside HTML websites and all kinds of backend code, they're everywhere. And in this example, we're creating a tree and then we're creating a function which sums up all of the values inside our tree. This is something that Recursion can do really well because with a tree structure, each branch of a tree can have other branches which can have other branches and so on, recursively. So Recursion is one of the best ways to calculate the sum of all of the values inside our tree. As for what we're actually doing, up here we're creating a tree node class and we're giving it a constructor which takes a value and sets the value of that instance of the class to your given value. It also attaches a children property to that instance and sets it equal to an empty array. Now below that we have our real recursive function. Now to explain how this is going to work, let's run through what we're actually doing to test our code. So down here we're creating a const variable called root and we're setting it equal to a new instance of our tree node class, giving it a value of 1. Now inside the children array of our new instance, we're pushing two new tree node instances, giving them separate values of 2 and 3. On the right, you'll see what this structure is looking like currently. And inside the first of these children, we're pushing yet another child node and we're giving it a value of 4. And finally, we're running the sum tree function of our root. So what we're trying to do is, if this works correctly, we can calculate the sum of all of our separate values inside each node of our tree. So how is this working? Looking at our sum tree function, the first thing it takes is our root node. So this is the node from which it starts summing up the values of all of the nodes below it. So inside our function, we're creating a let variable called sum and we're setting it equal to the value inside our given node. Next, we're running a for loop. For every child of our node children array, we're adding the sum of our parent node to the sum of all of the values of the children. Because the children nodes in a tree can have children of their own, that's why we need to run the same sum tree function on every single child until eventually there will be no more children to recursively hit against. At which point we can return sum and that will be the end of our execution. So for our given example, when sum tree function takes our root instance, the first thing it does is it sets our let sum equal to 1. Because remember, we set our value to 1. Next, it runs a for loop for every child of the children of our root. Remember, our root has two children, one with a value of 2 and one with a value of 3. Now our first child has a child of its own which has a value of 4, so when we run sum tree on that particular node, we are once again going to set sum equal to 4. We're going to run this for loop on the children of that node, and it turns out that node doesn't have any children, so we're going to return sum and then go back through the chain, adding up all of our values and eventually returning our final sum result, which we can confirm works by running this function and we get 10. And you can do the maths, that's 4 plus 3 plus 2 plus 1, which is 10. That's all from me on recursion. If there's any topics you want me to cover in the future, drop them down in the comments and I will see you next time.